Hi, and welcome to Allen High School's discussion of chemical bonding. We're going to jump right into our first type of bonding. The only reason it's first is because it's pretty quick to cover. We could also think about going in order of relative strength because in part we are doing that in this unit. So we're looking at network covalent, and recall from pre-AP chemistry that covalent bonding involves the sharing of electrons by two atoms. That's true of network covalent as well, but it differs from conventional covalent by the fact that it is long range. So it's long range, directional network of covalent bonds. So instead of just one covalent bond between carbons, there are many, many covalent bonds. It just goes on and on and on and on. And I know this doesn't look like it in my picture, but we could start to depict what is commonly called a girl's best friend, which is diamond. Diamonds are in a crystal structure. It's a long range, directional, fixed kind of network in a regular, this is important, very much like a crystal, regular, like a salt crystal is what I'm thinking of, predictable array. Now, if you think of diamond as kind of the penultimate example of network covalent bonding, you get an idea of the strength involved in these. These are not discrete molecules. For example, in sugar, we have a discrete molecule. We can call it C12H22O11. That's a discrete molecule with a defined beginning and end. That's not the case for network covalent. How many of each atom that is present depends on where you crack the molecule. So these are going to be much like ionic compounds. We're going to represent these as a formula unit. A prime example of that would be SiO2. We'll see that structure in a minute. That's silicon dioxide, sand, or glass. Okay, it's got a variety of common substances that can bring it to mind. And this is a formula unit. That's not just one silicon and two oxygens, as you'll see in the picture. The size, again, depends on when or where would be a better word than when. That macromolecule, I didn't leave myself much space there, so I'm going to shorten molecule MLCL. That macromolecule is fractured. Now, if you go into your book and you're reading this, the book will talk about band gap theory, and we're not going to cover that at this level. It's very important, but we're just not going to get into it at this point. We're going to see a table in just a minute that gives us some common examples, and you do want to memorize some of the more common. The first ones on the left, I want to get this word in here, are allotropes of carbon. Now, an allotrope, let me contrast that to a word you know, isotope. Isotope was the same protons, different neutrons. An isomer is the same molecular formula, but different structural formula. Okay, isomers, we'll come across those again in a little bit. Allotropes have the same element or maybe the same two elements, but different structures, and since structure determines function, they function differently as well. For example, graphite functions very differently than does diamond. So here's some structures. Here's all carbon. It's graphite form. And this is actually a little bit slippery. It can be used as a lubricant because these layers can slide past one another. This is diamond. It's very hard and very beautiful. And this is a whole series of molecules called fullerenes. And now scientists are working with nanotubes and using them for drug delivery and all sorts of very, very cool things. And they're carbon. So that's pretty cool. Graphite's a conductor. Diamond is not. give you another idea of how that structure determines function. This shows SiO2, and that's sand or glass. That's also used as an insulator in the semiconductor industry. If we want to change the properties of glass, we can dope it. This is a silicate. 8 indicates that it's some sort of an ion, a negatively charged ion, and you can see this far better in your notes than it's showing up here, but this shows sodium as a counter ion. Silicon carbide is another one, and so you really want to become quite familiar with these. So that is network covalent. In the next video, we're going to cover metallic bonding. So until then, this is signing off.